Okay, right. Let's dive in. We're looking at a market today that, most people probably don't think about much.
Yeah, kind of hidden away inside our gadgets.
Exactly. But it's totally crucial for the electronics we rely on, like every single day, keeping them running.
Absolutely. We're talking thermal interface materials, or TIMs, specifically for electronics cooling.
Right, Tim's. Think about, well, the chip in your smartphone, right?
Mhm.
Or your laptop processor.
Yeah, or even bigger stuff like servers in data centers, controllers in cars. They all generate serious heat.
And managing that heat is key. For performance, how long the thing lasts. Everything.
It really is. And to get a handle on this, we've been looking at a study from Cognitive Market Research.
Okay, so our mission here is what? To basically unpack the key numbers.
Exactly. Pull out the main trends from this source. We want to get a sense of the market size, how fast it's growing and where it's growing around the world.
Sort of understanding the unsung hero, keeping our tech from melting.
Huh? Yeah, something like that. It's foundational for the faster, smaller tech we all use.
Okay, so let's start with the big picture, the global view. What did this source say about the overall market size?
Right. So back in 2021, the global TIM market for electronics cooling was already pretty substantial, $1,738.23 million. dollars.
Okay, over 1.7 billion. And where's it heading?
Well, the projections show pretty strong growth. By 2025, just around the corner really, it's expected to hit $2,393 million. dollars.
Nearly 2.4 billion. That's quick growth.
It is, but the longer-term picture is even more striking, I think.
All right.
Looking out to 2033, the forecast jumps way up to 4,535.36 million.
Wow, okay. So over $4.5 billion. That's more than double the 2021 figure in, what, 12 years?
Exactly. And that kind of sustained expansion translates to an overall compound annual growth rate, a CAGR of 8.32%.
8.32% year over year for more than a decade.
Yep. For a market this size, that signals a really fundamental ongoing demand driver. It's not just a blip.
And the source points to, well, it seems obvious, but need for better cooling.
Right. Absolutely. The surging demand for efficient thermal management, like you said earlier, devices get faster, smaller, packed tighter.
And then just letting air cool them isn't cutting it anymore.
Precisely. You need these materials, Tims, to efficiently bridge the gap. They fill those tiny imperfections between, say, a hot chip and a heatsink.
Ah, okay. Like thermal paste or those little pads you sometimes see.
Exactly like that. Thermal pastes, pads, gap fillers. They ensure maximum heat can actually transfer away from the sensitive parts.
And that fundamental need is just growing across the board.
That's the core driver fueling this expansion, according to the source.
Okay, so strong global growth driven by the heat problem in modern electronics makes sense. But where's this growth actually happening? Regionally.
Good question. Yeah, the study breaks it down. And
Yeah.
it really highlights Asia Pacific. It's projected to have the highest KGR of all regions,
Oh, interesting. How high?
a pretty robust 8.969%.
Wow, nearly 9%. Okay, so what does that look like in dollar terms for APAC?
Well, they were already the largest region in 2021 at $636 million, roughly.
Right. That's projected to grow to about $880 million by 2025, and then really accelerate to over $1.75 billion by 2033.
$1.75 billion just in APAC. That is massive growth. I suppose that fits with the region's role in, making all this stuff.
And consuming it too, yeah, absolutely. Within APAC, China is, well, predictably huge.
Let me guess, the biggest single market.
By far. It was around $240 million in 2021, expected to hit $332 million in 2025, and then forecast to reach $688 million by 2033.
Almost $700 million just in China.
Wow. And Japan's significant too.
Right.
$76 million in 2021, growing to $102 million, then $195 million.
Okay. Any other standouts in APAC?
India shows really rapid growth. Started smaller, about $109 million in 21, but projected to hit $157 million in 25, and then a big jump to $324 million by 2033.
Seems like it. The source also detailed South Korea, Australia, Singapore, Southeast Asia as a group, Taiwan, all showing solid growth, contributing to that big regional number.
Okay, quite the powerhouse region. What about North America?
Still a major market, definitely growing. Its revenue was $462 million back in 2021.
Right.
Projected to reach $617 million by 2025, and then up to $1.13 billion roughly by 2033.
Over a billion. And the growth rate, the CAGR.
It's 7.84%, so slightly lower than APAC's rate, but still very healthy expansion.
And the U.S. must be the lion's share of that.
Yeah.
Silicon Valley, data centers. all that.
Absolutely. The U.S. market alone was $362 million in 2021, projected to hit $481 million in 2025, and then $874 million by 2033.
Okay. And Canada and Mexico.
They contribute significantly too. Canada goes from $57 million to $78 million, then $147 million by 2033. So strong demand across North America, likely driven by computing, telecom, maybe automotive too.
Yeah, that seems like a reasonable assumption, especially with more complex electronics going into cars now.
Makes sense. Okay, how about Europe? What's the picture there, according to the source?
Europe's another large established market. It was about $375 million in 2021.
Forecast to reach $502 million by 2025, and then expand to $939 million, almost a billion, by 2033.
And the growth rate for Europe.
The CAGR there is 8.125%. So, pretty much right in line with the global average. Healthy growth.
Does the source break down specific countries in Europe?
It does, yeah. It shows the breadth of the market there. Germany looks like the largest, going from $68 million in 21 to $94 million in 25, then $181 million by 33.
Okay, Germany's big.
And the UK is significant too. $39 million, then $54 million, projected $102 million.
Right.
But it also details France, Italy, Russia, Spain, the Nordics like Sweden and Denmark, Switzerland, Luxembourg. Quite a few.
So widespread demand across the continent.
Yeah, and the rest of Europe category is also quite large and growing, showing it's not just concentrated in a few spots, it's across the industrial and consumer sectors there.
Interesting. Okay, let's head south. What about South America?
Now, South America is actually pretty interesting, according to this study. It's starting from a smaller base, obviously.
Yeah, compared to North America or Europe.
Right. It was $108 million in 2021, but it's projected to grow quite fast to $172 million by 2025, and then $331 million by 2033.
$331 million. So what's the CAGR there?
It's 8.507%, which, according to the source, makes it the second fastest growing region after APAC.
Really? Faster than Europe or North America?
Based on this data, yes. Brazil is the biggest market there, going from $36 million to $59 million, then up to $115 million.
Okay.
Argentina is next, $13 million to $20 million, then $38 million. And it also mentions Colombia, Peru, Chile, all showing good expansion.
So what's driving that faster growth in South America, do you think? Just catching up or specific industries?
Could be a mix. Increased consumer electronics adoption, maybe building out telecom infrastructure, perhaps some local manufacturing kicking in too. The source doesn't specify drivers per region, but the numbers suggest strong momentum.
Got it. Okay, two more regions in the source data, right? Middle East and Africa. What about the Middle East?
Right. Middle East, again, smaller base globally, but showing steady growth. It was $85 million in 2021. Projected to grow to $117 million by 2025, and then reach about $199.5 million by 2033.
And key countries there.
The source highlights Saudi Arabia as the leader, growing from $34 million to $47 million, then $80 million. Turkey is also significant, $20 million, then $27 million, up to $46 million. And it lists the UAE, Egypt, Qatar, too, all contributing.
So likely driven by IT infrastructure spending, maybe diversification efforts?
Yeah, it would make sense, yeah. Investments in tech across various sectors seem likely drivers.
Okay, and finally, Africa.
Africa's TIM market was pegged at $71 million in 2021.
Right.
Projected growth takes it to $103 million by 2025, and then $186 million by 2033. Again, starting smaller, but showing potential.
Yeah, and the main contributors.
The study gives figures for Nigeria and South Africa primarily. Nigeria grows from $17 million to $25 million, then $47 million.
Okay.
South Africa is noted as the larger market within the region, going from $30 million to $43 million, then projected $77 million. And the rest of Africa also makes up a decent chunk of that growth.
Okay. So if we pull all that together,
Yeah.
what's the main takeaway from this cognitive market research study?
Well, the big picture is definitely one of broad-based, sustained growth everywhere.
Yeah, it really seems like it. Strong expansion projected from 2021 right through 2033, not just globally, but across every single region we discussed.
From the big manufacturing hubs in APAC, the established tech markets in North America and Europe,
All the way to the faster-growing developing markets in South America, the Middle East, and Africa. It's universal.
and it all seems to tie back to that core driver the source mentioned. Electronics just keep getting more powerful, smaller, and hotter.
Right, which means the need for these often invisible materials just keeps increasing.
Exactly. They're fundamental to making modern tech work reliably.
It really highlights how crucial these specialized bits and pieces are. Okay, so wrapping this up.
Yeah, looking at these numbers definitely makes you think about what specific tech is driving this surge.
Right. So, the final thought for you listening, considering this global market is set to more than double over the next decade, and we see these different growth rates playing out across the world, what specific types of electronics or maybe what tech trends do you think are really pushing this massive demand for better thermal management materials right now? Something to chew on.
Okay, so uh, today we're diving into something, well, it's pretty crucial, maybe even fundamental to almost every electronic device you use, even if you've, never really thought about it before. We're talking about thermal interface materials, TIMs.
That's right, TIMs. They're kind of the quiet support crew inside your tech.
Unsung heroes, maybe.
Exactly. While you hear all about the super fast processors or the graphics cards, these materials are working away in the background doing a really critical job,
Which is?
basically filling the gaps. You've got a hot component like a chip and a cooling device like a heat sink. But on a microscopic level, those surfaces aren't perfectly flat. There are tiny air gaps.
Ah, right. And air doesn't conduct heat very well, does it? It's more of an insulator.
Precisely. So these TIMs, they fill those gaps with something that does conduct heat well: grease, pads, sometimes more exotic stuff. It lets the heat flow efficiently from the hot part to the cool part.
Keeping things from overheating,
Yeah.
which is obviously important. Stops your laptop burning your lap, for one thing.
Well, yeah, but it's more fundamental. Too much heat kills performance, it shortens the lifespan of components, and it can cause outright failure, catastrophic failure sometimes.
Okay, so our mission for this deep dive, Zen, is to really unpack this market report you shared. Get into the weeds on TIMs.
Yeah, we want to understand what's driving the demand why now. What are the big challenges or roadblocks, and what's coming next? What are the key trends?
And hopefully show how these, tiny bits of material actually have a massive impact on the tech we use every day.
It's pretty surprising when you dig into it.
So where do we start? The report talks about driving forces. What's the number one reason TIMs are so critical right now?
I'd say the biggest one is just the relentless push for smaller and more powerful electronics, miniaturization, and increasing heat density.
Right, cramming more and more power into smaller and smaller boxes.
Exactly. Think about high-end gaming laptops
Hmm.
or VR headsets. They're packing incredible processing power into really tight spaces.
Or 5G base stations. The report mentions those too.
Yeah, same deal. Lots of power, often in compact units. The amount of heat generated per square inch or cubic inch, it's immense compared to older tech.
So without good TIMs,
You get thermal throttling, where the device deliberately slows itself down to avoid meltdown. Or worse, it just overheats and fails.
so TIMs are basically essential for performance and keeping the thing alive.
Absolutely. Performance and reliability hinge on getting that heat out efficiently.
And it's not just gadgets, is it? The report flags huge demand from data centers and high-performance computing, HPC.
Oh, definitely. Data centers are massive energy consumers. And a huge slice of that energy pie goes just to cooling all those servers.
Right, trying to keep those racks and racks of computers from cooking themselves.
So a major goal for them is cutting that cooling energy cost, and this is where advanced TIMs really shine. The report mentions things like nanocomposites, even liquid metal interfaces.
Liquid metal, wow, okay.
Yeah, pretty cutting edge stuff. These materials drastically reduce what's called thermal resistance.
And making it much easier for heat to transfer.
Exactly. Think of it like turning a bumpy dirt track for heat into a multi-lane superhighway. Heat just flows away much more easily.
Which means the air conditioning or liquid cooling systems don't have to work quite so hard.
Precisely. Less work for the cooling system means less energy used, better energy efficiency, lower operating costs, smaller carbon footprint. It's a big win for them.
Makes sense. Huge potential savings there. Where else is demand really taking off?
Another massive area is electric vehicles, EVs,
Yeah.
and automotive electronics in general.
Okay, how so? Batteries? Motors?
All of the above, really. Think about the power inverters, the battery packs themselves, which generate significant heat during charging and discharging, the onboard chargers, even the complex ADAS systems, the driver assistance tech.
Lots of powerful electronics packed in there.
And in a car, efficient heat dissipation isn't just about performance or lifespan, though it's key for those too. It's fundamentally about safety. You cannot have critical components overheating.
Non-negotiable, basically.
Absolutely. So TIMs are playing this vital, hidden role in keeping EVs safe and reliable.
The report even mentions renewable energy systems.
Yeah, it does. Things like solar inverters, which convert the DC from panels to AC for the grid or your house. Or the controllers inside wind turbines.
The generate heat, too.
They handle a lot of power, so yes, they do. And they often operate in harsh outdoor environments. Good thermal management, helped by effective TIMs, keeps them running efficiently and helps them last longer. Better ROI on the green energy investment.
Okay, so the drivers are pretty clear. Miniaturization, data centers, EVs, renewables. These are all huge growing sectors pushing demand. But the report also points out some pretty significant roadblocks. It's not all easy. What are the main challenges?
Yeah, there are definitely hurdles. Probably the biggest, most persistent one is cost, especially for the really high-performance TIMs.
Like the liquid metals you mentioned, or graphene.
Exactly. Materials like graphene, silver particle-filled compounds, liquid metals, they offer fantastic thermal performance, but they are significantly more expensive than, say, your standard silicone-based thermal grease or basic pads.
So you get what you pay for, but the price is high.
Right. Which means their use often gets limited to, premium applications. Aerospace, maybe some high-end computing, luxury electronics, mainstream stuff. Often still relies on the older, cheaper, less effective materials. It creates a sort of performance ceiling dictated by budget.
Interesting. Okay, cost is one. What else? The report mentioned durability issues.
Yeah, that's a really important one. TIMs aren't necessarily a fit-and-forget solution. They can degrade over time.
How does that happen?
Several ways. Repeated heating and cooling cycles, thermal cycling, can physically stress the material. Mechanical pressure or vibration can cause issues, sometimes oxidation if they're exposed to air. This leads to problems like, the report calls it pump out.
Pump out, like it gets squeezed out.
Kind of, yeah. The expansion and contraction can slowly push the material out from between the surfaces it's supposed to connect. Or you get dry out, where volatile components in the TIM evaporate over time, leaving it less effective, maybe even crumbly.
I think I've maybe seen that. Like an old PC or laptop starts running hotter than it used to. Could that be the TIM failing?
It absolutely could be a contributing factor. As the TIM degrades, its ability to transfer heat drops, sometimes quite significantly. So yeah, performance suffers, or you might need to replace the TIM, which means maintenance costs.
Definitely a hidden factor there. And the third is big challenge the report highlights is application complexity.
Yes. This is particularly true for some of the more advanced TIMs. They can be fussy.
Fussy how?
Some need really specific conditions during manufacturing, maybe precise curing temperatures or times, or they need to be applied to achieve a very specific thickness, a certain gap width.
Tricky to get right on a mass production line, maybe.
It can be, and getting it wrong is risky. Apply it badly, and you might actually increase the thermal resistance by trapping air. Or worse, with electrically conductive TIMs.
Like the liquid metals again?
Yeah, or some filled greases. If they squeeze out or get somewhere they shouldn't, they can cause short circuits. Big problem.
Ouch. Yeah, that would be bad. So that adds complexity, cost, and risk to the manufacturing process itself.
Exactly. It limits which manufacturers can effectively use these advanced materials, or it pushes up the end product cost.
Okay, so we have this tension. Huge demand driven by massive tech trends, but facing hurdles like cost, long-term durability, and tricky application. So where does that leave us? What's the future look like? The report talks about key trends in TIM innovation. What's happening?
Well, one of the really exciting areas the report emphasizes is nanotechnology.
There's incredibly small materials, like atoms level small.
Pretty much. We're talking materials engineered at the nanoscale billionths of a meter. Things like graphene, which is like a one-atom thick sheet of carbon or carbon nanotubes. Incorporating these nanomaterials into TIM formulations can dramatically boost thermal conductivity.
Though better heat transfer.
Much better. And often you can achieve that with incredibly thin layers, which is perfect for today's compact devices. Plus, they can sometimes add flexibility.
Thin and flexible. Sounds ideal. Now, we mentioned liquid metal TIMs as being expensive and tricky, but the report also lists them as a key future trend. Seems a bit contradictory.
It does, but it's about where they're being targeted. Despite the challenges, their performance is just exceptional. Especially gallium-based alloys, their thermal resistance is ultra low. So for the absolute most demanding applications, think leading-edge CPUs, GPUs, maybe extreme overclocking scenarios where every single degree Celsius matters.
That's where they make sense, despite the cost.
That's where the demand is growing, yes. The performance benefit outweighs the downsides for those specific high-value uses.
Gotcha. Okay, what about phase change materials? The report mentions those too. How are they different?
Phase change materials, or PCMs, are pretty clever. They have this unique property. They're typically solid at room temperature.
So easier to handle, like applying a solid pad.
Exactly. Easier to apply during manufacturing, less messy than a grease, perhaps. But the key is, when the component they're cooling heats up to its normal operating temperature, the PCM melts. It transitions to a more fluid state.
And why is that good?
Because in that fluid state, it flows into and fills all those microscopic imperfections on the surfaces of the chip and the heatsink. It eliminates virtually all the air gaps.
So it conforms perfectly once it gets hot.
Right, leading to really low thermal resistance when it matters most. They're becoming quite popular, especially in high-performance computing and servers.
That makes a lot of sense. Thinking about weird shapes again, the report also talks about flexible and even stretchable TIMs. Sounds like wearables, foldable phones.
You're spot on. As electronics move beyond rigid boxes, think wearable sensors, flexible displays, electronics woven into fabric. You need TIMs that can cope with that. They need to maintain their thermal performance even when they're being bent, stretched, or crammed into really tight, non-flat spaces. Developing materials that can do that and conduct heat well is a big area of research.
Fascinating. And is there an environmental angle? Are TIMs getting greener?
There's definitely a push, yeah. Driven partly by regulations like RoHS or REACH, but also by consumer and corporate demand for more sustainable products. So manufacturers are working on formulations that are non-toxic, maybe biodegradable, and have low VOC content,
VOC.
volatile organic compounds. Basically, chemicals that can easily evaporate and potentially cause air pollution or health issues. So moving to low VOC or zero VOC TIMs is becoming more important.
Good to hear. And finally, the report mentioned integration, like TIM's working with other cooling stuff.
Yeah, it's not just about the TIM in isolation anymore. There's a trend towards designing the TIM as part of a whole thermal management system, thinking about how it interfaces with, say, advanced heat pipes or vapor chambers or even liquid cooling loops.
So optimizing the TIM makes the whole cooling solution work better.
Exactly. If you can get the heat across that initial interface really efficiently with a great TIM, it gives the rest of the cooling system, the heat pipes, the fans, the radiator, a better chance to dissipate it effectively. This kind of synergy is crucial in those really high power density situations we talked about. Gaming, 5G, servers.
Right. Okay, so stepping back from all the details, this deep dive really underlines that TIMs are, well, they're anything but simple filler material.
Not at all. They're evolving incredibly fast. They're being constantly pushed by the demands of miniaturization, by the sheer power density in data centers, by the safety requirements in EVs, even by renewable energy growth.
They really are those unsung guardians, aren't they?
Mm.
Quietly working away to make sure all our complex tech performs well and stays safe. From, keeping a simple video call smooth on your laptop.
To ensuring the massive battery in an electric bus operates reliably for years. It's a huge range of applications, all relying on effective heat transfer at that critical interface.
Yeah. It really puts them at this crossroads, doesn't it? Between the relentless drive for more performance and the fundamental physics of heat. Which kind of leaves us with the final thought, maybe something for you, the listener, to chew on. As you look at the devices around you and think about what's coming next, how do you see this balancing act playing out? The push for ever higher performance demands these advanced, sometimes tricky, expensive TIMs. But we also have the real-world constraints of cost, durability, and manufacturing complexity.
Yeah, how will that tension shape the next generation of electronics? Will we see breakthroughs that make high-performance TIMs cheaper and easier to use? Or will thermal limits, partly dictated by TIM technology, start to put a brake on performance gains or make cutting-edge tech less accessible?
That's something to think about. How will that balance affect the design, the power, and maybe even the price tag of the gadgets you'll be using in the near future?